There's a cosmic void. It's so large it actually chills the space around it. This isn't about a black hole. It's about an emptiness. A staggering emptiness that defies our basic understanding of the cosmos. This vast nothingness challenges the very foundations of modern cosmology. Astronomers found it. They found this freezing abyss in the ancient light of the universe. And there's a bizarre physics at work. A physics that allows emptiness to have a gravitational push. So what does it tell us? A hole in reality, billions of light years wide. What does it tell us about the ultimate fate of everything? The emptiness is the rule. Most of the cosmos isn't brilliant stars or swirling galaxies. It's vast, sprawling tracts of almost nothing. You can think of the universe like a sponge. The solid, dense parts are the great walls and filaments, the cosmic web. But the holes in that sponge, those are the voids. And they are not small. A typical void can stretch for hundreds of millions of light years. And inside that volume, you might find just a handful of lonely galaxies. Sometimes none at all. These are the deserts, the great silent expanses that dominate the volume of everything. For a long time, science saw them as just that. Passive, empty backdrops. The real action was in the clusters and superclusters, but that view has changed completely. We understand now that voids are not passive. They are dynamic, evolving regions. They actively shape the fate of the universe. Their immense gravity, or really, their profound lack of it, acts like a cosmic vacuum cleaner, slowly pulling matter away from their centers, toward the dense, galaxy-rich edges. This process influences everything. How galaxies form, how they move. How the entire large-scale structure of the cosmos evolves over billions of years. So a void isn't a simple hole. It's a dominant feature of reality. A colossal emptiness with its own strange physics, its own profound influence. And within this category of cosmic giants, there is one void, exceptionally vast and empty. It does something no other void has been observed to do. It chills the very fabric of space around it, that cold spot in the cosmic background. Astronomers had mapped that ancient light, the afterglow from when the universe was very young. It's incredibly even, a smooth thermal blanket. But there was a blemish, a patch of sky much larger than you'd expect, where the temperature of that light was just a bit colder. A tiny difference but real. The CMB cold spot, and its existence was a puzzle. If the early universe was so uniform, what could cast such a long, cold shadow across billions of years? The hunt for an explanation. The leading theory pointed to an absence, an enormous void, a vast region where matter is depleted. The idea uses a piece of physics called the Integrated Sachs Wolfe effect. Think of a photon from that ancient light starting its journey. For most of the trip, the gravitational pull from clusters and the push from voids balance out. But in the last several billion years, dark energy began to dominate the expansion. That changes things. As a photon enters a vast, growing void, it climbs out of a gravitational well. But the well is becoming shallower over time because dark energy is stretching the void larger. The photon expends energy to escape, and it gets less of that energy back than it should. So the photon arrives slightly drained, stretched to a longer, colder wavelength. It carries the chill of the void. So astronomers turned from the ancient light to the modern universe. They cross-referenced the cold spot with surveys charting millions of galaxies. And there, in Aridanus, they found it. A staggering emptiness, a proposed supervoid, maybe over 1 billion light years across. Not just a cosmic desert, a super desert, so vast that its gravitational landscape, shaped by dark energy, could imprint that cold signature onto the primordial light. The Aridanus supervoid, its identification was a revelation. It meant these colossal nothings were active players, leaving fingerprints on the first light of creation. A void had become a direct, observable phenomenon, its shadow stretching from the dawn of time to our telescopes. The numbers are too big to really understand. So think of it this way. Picture our galaxy, the Milky Way, Hundreds of billions of stars. Now shrink that down to the size of a grape. In that scale, our local group of galaxies, Andromeda and the others, that's just a fruit bowl on a table. That's our neighborhood, and a normal cosmic void, one of the empty deserts, that would be like an empty warehouse around that little table. A huge space of nothing around our little island. But this void we're talking about, it's not a warehouse. On that same scale, it's an empty continent. You could walk for a lifetime and never see another soul, never find another table or bowl. This supervoid is estimated to be 1.8 billion light-years across. You could travel at light speed for nearly 2 billion years and find almost nothing. No galaxy clusters, no great walls, just emptiness, and that scale, it's significant. The void is so big that light from one side hasn't had time to reach the other side since the universe began. So parts of this single structure are causally disconnected. They can't have influenced each other. They're separate islands of emptiness inside a bigger sea of nothing. It's one thing, but it exists in pieces that have never been in contact. That size, that incomprehensible size, is the first key. Because it's that scale that lets the void do something extraordinary. It's not just empty space. It's an emptiness so vast it starts to warp space-time and energy around it. And that's what creates the signature we saw, that cold spot from the dawn of time. An emptiness makes things cold because of what happens to ancient light on its journey. That light, the cosmic background radiation, is a snapshot from when the universe was hot and dense. It's been traveling for over 13 billion years to reach us, and on that trip it passes through everything: galaxies, clusters, and vast, empty voids. In those voids, something subtle happens to the light. It's called the Integrated Sachs Wolfe effect. It's a gravitational trick that happens because the universe isn't static. It's expanding, and that expansion is accelerating because of dark energy. Picture a single photon of that ancient light approaching a huge void. As it enters this region of low gravity, it's like rolling downhill. It gains a tiny bit of energy, but then it has to climb out the other side. That's the crucial part. As it climbs out, it's fighting the void's gravitational pull. In a static universe, the energy it gained going in would equal the energy it lost climbing out. It would be a wash, but our universe isn't static. While that photon is inside the void, over millions of years, dark energy is at work. It causes the void itself to expand and stretch, making its gravitational well shallower, weaker. So when the photon finally climbs out, the hill isn't as steep as when it entered. It loses less energy than it gained. That sounds like a net gain. The photon should arrive with more energy. But here's the twist of general relativity. In an expanding universe dominated by dark energy, the opposite happens. The photon actually loses a net amount of energy during the entire trip. Think of it like pushing a heavy box across a floor that's slowly turning to ice. You push hard to get it moving, but as you keep pushing, the friction vanishes. The ground gives way. Your effort is wasted, and the box doesn't get the momentum you intended. For the photon, that wasted effort is energy lost. This loss of energy means the photon's wavelength gets stretched. It shifts toward the red, cooler end of the spectrum. It arrives just a little bit colder than light that traveled through denser regions. For a single photon, this effect is vanishingly small. But the Aridanus supervoid is not small. It's staggeringly vast. A photon might spend hundreds of millions of years crossing its emptiness. Over that immense distance, that tiny energy loss adds up. It accumulates, and when we look at the collective light from that patch of sky, we see the sum of all those slight coolings. We see the cold spot. So the void doesn't have a temperature itself. It's not blowing cold air. Instead, it acts as a cosmic filter, a lens that saps a specific amount of energy from the oldest light. The chilling is a signature, a direct imprint of the void's immense scale and the accelerating expansion of everything, written in the faint chill of primordial light. This observation connects three things: the largest structures in existence, the first light of creation, and the mysterious force of dark energy that shapes our cosmic fate. The chilling effect points to something deeper. A kind of paradox. We think of gravity as attraction, mass pulling on mass, so a void with less mass should have less pull, and that's right. But in this universe, less gravity can sometimes feel like a push. That's the paradox. Inside that billion light-year void, the normal matter is so sparse it stops being the main force. Something else takes over, dark energy. This thing that fills all of space, making the universe expand faster. It acts like anti-gravity on the biggest scales. In crowded places like galaxy clusters, all that matters gravity holds its own against the push. It's a standoff, but in the deep emptiness of the void, there's no competition. The matter is almost gone, so dark energy works almost alone. Space itself expands faster inside the void than outside in the denser parts. So the void isn't just empty. It's a place where the emptiness is actively growing, stretching faster. Think of the universe like a stretching sheet. And one part of the sheet is thinner, weaker. When you pull, that thin spot stretches more. It balloons out faster than the thicker parts around it. That's the void. Its interior isn't still. It's a region of hyper-expansion, and that leads to a strange gravitational effect. From the edge, from a galaxy sitting there, it feels like the emptiness is pushing it away. The void isn't pulling things in, it's pushing things out toward the dense walls around it. That's why voids clean up matter, not by sucking but by repelling. Their accelerated expansion herds matter toward the cosmic web. This stretching, this dynamic change inside the void, is the last piece. The photon losing energy as it climbs out. That energy loss is tied to how the void's gravity changes over time. Because the void is expanding faster, its gravitational well isn't just shallow. It's getting shallower at an accelerated rate while the photon is trying to escape. The photon is climbing a hill that's flattening under it. It loses even more energy. That extra loss, that extra cooling, is the direct mark of the void's push. The cold spot isn't just a fossil of an old emptiness. It's a living record. An emptiness that's actively stretching the cosmos from the inside. But this huge scale brings up the fourth mystery. Is the void just too big? Our main map of the universe is the Lambda-CDM model. It's a framework from decades of work. It describes a universe with dark energy, cold dark matter, and normal matter, and it makes predictions. One big one is about the texture of the cosmos. The universe should have a certain graininess, a statistical pattern to how things are arranged, like the grain in wood. You expect knots and patterns of a certain size, spread out in a predictable way. Voids are part of that grain. But in the model's simulations, a void this big, a supervoid almost 2 billion light-years across, is an extreme outlier. It pushes right to the edge of what the standard model says should be possible. Finding it was like finding a single, perfect knot in a piece of wood that's bigger than the whole tree. So astronomers had a puzzle. Is the Aridanus supervoid just a rare fluke? A 1 in a million roll of the dice that happened in our part of the universe? Or does it point to something deeper, something missing from our math? The chance of a statistical anomaly is always there, but its alignment with the cold spot makes that chance seem smaller. It feels like more than coincidence. That's led scientists to think about more exotic ideas. Maybe our understanding of the Big Bang's starting conditions is incomplete. Maybe the seeds for such vast emptiness were planted in the universe's first moments, through processes we haven't thought of yet. Some theories go even further. Could this colossal void be a scar? The imprint of a collision between our universe and another bubble universe in a wider multiverse? Or a fossil from before the Big Bang? A relic of a physics that operated before time as we know it began? These are speculative, but they show how deeply this anomaly challenges us. It questions the principle of homogeneity on the largest scales, the idea that the universe should look roughly the same everywhere when you zoom out. This void suggests our cosmic map might have unexplored continents of nothing, regions so vast they change what we think is normal. It makes us ask if our standard model, successful as it is just a map of the local neighborhood, while beyond it there's a geography we're only starting to see. Mapping a void means mapping what isn't there. You can't just look at the emptiness. You have to map everything around it in detail to see the shape of what's missing. The main tool for that is a galaxy redshift survey, something like the Sloan Digital Sky Survey. It spent decades scanning the sky, not just taking pictures, but getting the spectra of millions of galaxies. That spectrum gives you the redshift. The light is stretched because the universe is expanding. A bigger redshift means the galaxy is farther away. So you turn a flat star chart into a three-dimensional map. You get depth. You get latitude, longitude, and cosmic time. Then you plot all those millions of points in a computer model, and the structure appears. The cosmic web. Great walls of galaxies, filaments, dense nodes where they intersect. And between them, the voids. They show up as huge, spherical bubbles. Places where the dots just disappear. The map is really defined by its gaps. To confirm a supervoid like the one in Aridanus, that galaxy map is just the start. Astronomers lay another map over it. The map of the cosmic microwave background from a satellite like Planck. They look for the alignment, a cold spot in that ancient light, overlapping exactly with a huge emptiness in the modern galaxy map. That correlation is the evidence. There are even subtler methods. Weak gravitational lensing. A void, even with its lack of mass, has a gravitational signature. It's like a hill of negative gravity. Light from galaxies far behind the void passes through this region, and its path gets bent, just slightly. Not pulled inward, but pushed outward around the edges of the emptiness. By studying the tiny, coherent distortions in the shapes of thousands of those distant galaxies, scientists can trace the void's gravitational footprint. They can weigh the absence. These tools together, the redshift surveys, the CMB maps, the lensing studies, they work like a kind of cosmic sonar. We send out observations and listen for the echoes that come back from the edges of nothing. The contours of the void slowly come into focus. This cartography of absence isn't just academic. It's necessary. To understand the universe, you have to understand its full anatomy. Not just the bones, but the spaces between them. The voids aren't accidents, they're foundational. By mapping them, we learn that what isn't there shapes everything that is. The distribution of galaxies, the flow of cosmic motion. Even the fate of the universe is written as much in these great emptinesses as in the stars. That ancient light is our most direct link to the beginning. The cosmic microwave background. It's not a picture of stars. It's a picture of the universe itself, at the moment it became transparent. 380,000 years after the Big Bang, the hot plasma of particles and light finally cooled enough for atoms to form. And the light, which had been trapped, bouncing around, was suddenly set free. That first flash has been traveling ever since, stretched by the expansion of the universe from visible light into microwaves. It's a fossil, but a living one. It fills every point in the sky, a whisper from the dawn of time. Its most stunning feature is its uniformity. No matter where you look, the temperature is almost exactly the same. 2.7 degrees above absolute zero. This smoothness tells us the early universe was a remarkably even place, but almost is the key word. Embedded in that smooth background are tiny ripples. Minuscule variations in temperature, just 1 part in 100,000. These anisotropies aren't flaws, they're the seeds of everything. The slightly denser, warmer spots in that ancient soup were the gravitational seeds. Over billions of years, they pulled in matter to form galaxies, clusters, the great cosmic web. The slightly cooler, emptier spots were the seeds of the voids. So this canvas is a detailed blueprint, a map of the initial conditions of the entire cosmos. The cold spot associated with our supervoid is one of the most prominent features on that map. It's a large, statistically significant patch of cooler temperature. Finding it was like discovering a unique fingerprint pressed into the surface of that ancient light. It stands out. It asks for an explanation, and this is where the CMB transforms from a static relic into an active tool. Think of it as a backlight, a uniform sheet of light shining from behind the entire universe. As those 13 billion-year-old photons travel toward us, they don't travel through empty space. They pass through the evolving large-scale structure of the cosmos. They climb in and out of the gravitational wells of clusters, and they pass through the expansive, shallow hills of the voids. Each encounter leaves a tiny mark. A subtle shift in the photon's energy, a slight change in its temperature. By the time that light reaches our telescopes, it carries an imprint, a story of everything it passed through. The cold spot is a chapter in that story. It's the collective signature of billions of photons that spent a significant part of their journey traversing an immense region of accelerating emptiness. Their energy was subtly drained, their wavelengths stretched by the dynamic gravity of the void. So we're not looking at the void directly in the CMB. We're reading its shadow, its effect on the oldest light there is. This makes the cosmic microwave background a powerful diagnostic tool. By decoding these patterns of hot and cold, these tiny temperature variations, cosmologists can do something extraordinary. They can infer the distribution of matter, both seen and unseen, across the vast history of the universe. They can chart where the great masses gathered and, just as importantly, where they did not. The cold spot is a direct pointer. It tells astronomers where to train their three-dimensional galaxy surveys to find the corresponding emptiness. It connects the universe's first moment to its present-day architecture, using a whisper of cold as the guiding thread. The link between emptiness and acceleration is the key to what comes next. Dark energy, this strange force, it doesn't just exist in the universe. It takes over in the places where there's almost nothing else. Where matter is thin, its repulsive push has nothing pushing back. That makes cosmic voids, the really huge ones, into something special. They're dark energy's playground. Its main lab. Inside a supervoid, the usual gravitational pull from matter is barely there. There's nothing to slow the stretch. So space itself expands faster inside the void than it does out in the crowded filaments and clusters. The void isn't just an empty bubble. It's an accelerator, a place where the fabric of reality is being pulled apart more forcefully than anywhere else. By seeing how these voids grow and change over cosmic time, scientists can run a crucial test. They can measure the strength of dark energy's influence in its purest form. Is it constant, like Einstein's cosmological constant? Or does its strength shift over time, pointing to something more complex? The evolution of a void gives a direct answer. If dark energy's push is constant, a void will expand at a steady, predictable rate. But if the force changes, the void's growth would speed up or slow down in ways simple predictions can't account for. This is where a void like the one in Aridanus becomes so valuable. Its extreme size and deep emptiness make its behavior a magnified signal. Any subtle effect of dark energy would be written large across its billion light-year span. Studying it is like putting the most sensitive instrument right into the heart of the mystery. The way its edges move, the rate its interior empties out even more, even the specific chill it leaves on the cosmic background. All these are data points in the big experiment to understand the force that controls our fate. So this cold void is much more than a curiosity. It's a window, a natural observatory built into the structure of reality, designed to light up the shadowy driver of everything. By looking into its depths, we're not just seeing an absence. We're watching the main mechanism of the future, the force that will finally decide if the universe expands forever into a cold, dark silence, or finds some other destiny. The answer is in the emptiness. That emptiness, it creates a frontier, a shoreline between two worlds, and for the galaxies that form that boundary, life is shaped by the void right at their doorstep. They aren't floating freely in the emptiness. They cling to the dense filaments, the great walls. They're the last outposts of structure before the cosmic desert begins. Their existence is defined by this edge. The void's repulsive gravity, that strange push from the accelerated expansion, it exerts a force on them. Astronomers call it a peculiar velocity. It means these galaxies aren't just moving with the general flow of the universe's expansion. They're being nudged, ever so slightly, away from the void's center. Toward the denser web around them, they're being herded by the emptiness. This environment changes everything about how a galaxy lives and grows. In the crowded heart of a cluster, galaxies are social. They swing past each other, sometimes merging in colossal collisions. That triggers bursts of new stars, it reshapes entire structures. But on the void's frontier, a galaxy is isolated. Its nearest major neighbor might be millions of light-years away across the gulf. This solitude means a quieter life, a slower life, with no frequent mergers to stir things up. Star formation can proceed at a more gradual pace. A steady pace. Some theories suggest these frontier galaxies could be relics, older systems that have evolved in peace for eons. They might preserve a chemical composition that's less polluted. Less polluted by the violent influx of gas from mergers. They're the cosmic equivalent of a secluded island ecosystem, evolving on its own unique path, untouched by the continental shifts happening elsewhere. Studying these galaxies is like taking a core sample from the edge of the universe's largest feature. By examining their ages, their motions, the types of stars they hold, astronomers can read the history of the void's influence. They can see how the relentless push from the emptiness has sculpted this borderland. Over billions of years, the void's edge isn't a sharp line, it's a gradient. A zone of transition where the pull of the cosmic web and the push of the void are in a delicate balance. This makes it a unique laboratory. Here, scientists can observe galactic evolution in its most extreme environmental context. Not in the dense urban centers of the universe, but in the quiet, wind-swept towns on the edge of the Great Desert. What they learn rewrites the rules. It shows that a galaxy's fate is written not just by what is around it, but by what is profoundly absent, staggeringly absent. The leading explanation is compelling. But it might not be the final word. The cold spot is so extreme, it's inspired other ideas, more exotic ideas. Each one pushes at the edges of known physics. One concept involves cosmic textures. Picture the early universe cooling down from an unimaginably hot state. As it cooled, the fundamental fields might have frozen into place unevenly. That could create defects, not cracks but topological knots, knots in the fabric of spacetime itself. A cosmic texture would be a point where space is twisted. It creates a unique gravitational field. If one existed between us and the cosmic microwave background, light passing by would lose energy. That would leave a cold, circular imprint on the sky. It's a 1 in a billion possibility, but if it's true, it would be a direct fossil, a snapshot from the universe's first moments, physics at energies we can never recreate. Another avenue looks at unseen mass. Could a colossal foreground object be acting as a lens, a supercluster of galaxies and dark matter we haven't fully mapped? It would bend the paths of the CMB photons, distorting the pattern, cooling it. But detailed surveys haven't found a structure large enough or in the right position to produce such a pronounced effect. That absence just deepens the puzzle. Then there are ideas that step outside our cosmic box. Some models suggest the cold spot could be a bruise, the imprint of a collision between our universe and another bubble universe in a wider multiverse. In that scenario, the contact between two separate realms in their earliest moments could have left a lasting mark. An anisotropic mark on our sky. It's a breathtaking speculation. It transforms the cold spot from a cosmic anomaly into a potential window. A window into a reality vastly larger than our own. This diversity of thought isn't a weakness in cosmology. It's its greatest strength. The cold spot resists a single, tidy explanation. It sits at a crossroads. Between observation and theory, between the mapped and the unknown, each proposed idea carries profoundly different implications: supervoids, space-time knots, multiverse collisions. They each imply different laws. This healthy uncertainty is what drives science forward. The most intriguing mysteries refuse to be solved with existing tools. They force us to question our assumptions, to dare to imagine wilder, more fundamental truths. The cold spot does exactly that. It reminds us, the universe's deepest secrets are often written in the subtlest signatures. Waiting in the quiet chill of ancient light, these questions need a place to be tested, a place to run experiments on the universe. Since we can't change the cosmos itself, we build a copy. A digital twin. Cosmologists build entire universes inside supercomputers. These aren't animations, they're n-body simulations, mathematical worlds that follow the laws of physics. They start with a soup of particles, representing dark matter, normal matter, dark energy. They set the starting point using the cosmic microwave background. Those early ripples. Then they press play, and the simulation runs for billions of years of cosmic time in just weeks or months. Each particle's gravity pulls on all the others. Structure begins. In these virtual spaces, we watch the cosmic web form. Galaxies gather along filaments, and between them, huge voids appear naturally. They aren't put in. They grow from the physics, from gravitational pull and the push of expansion. Famous runs like the Millennium Run or Illustris TNG have become their own fields of study. They make detailed maps of these digital universes, maps we can compare to our own. That's the test. By looking at the voids in the simulations, scientists can ask statistical questions. How many voids of a certain size should exist? What's the average temperature mark they leave on their virtual background? How often does a void become a supervoid, 1.8 billion light-years wide? When they compare, the Aridanus supervoid sits at the edge. In most simulations, a void that large and that empty is rare. Maybe 1 in 100, 1 in 1,000. But it's not impossible. The standard model doesn't rule it out. It just says a giant like that would be exceptional. That statistical tension is where the mystery is. Is our universe showing us a rare but possible roll of the dice? Or does this giant void and its cold spot suggest the dice are loaded, that our simulations, accurate as they are, might be missing something? These digital sandboxes allow for experiments. Scientists can change the parameters. They can increase dark energy's strength, or change the dark matter particle, or alter the initial seed patterns from the Big Bang. Then they run it again, and they watch. Does the change make more supervoids? Do those supervoids create colder spots? By repeating this, they see which versions of physics make a cosmos that looks most like ours. It's a process of elimination on a universal scale. So the simulations do more than test theories. They become tools for discovery. They let us explore cosmic what-ifs in a controlled way. They let us look into emptiness not just as observers, but as architects of possible worlds. The fact that our best digital universes can sometimes create a void as vast as the one we see is reassuring. It means our basic map of reality is mostly right. But the fact that it stays a stubborn outlier, a statistical whisper at the edge of prediction, is what keeps the search going. It means the next big discovery might not come from looking deeper into the sky, but from refining the code of a universe inside a machine. The emptiness is so large, it pushes us past the equations, past the data. A void like this isn't just a structure, it's a mirror. It shows us a universe that is fundamentally indifferent. We have our stories, our myths. We look for meaning out there, for companionship, but the data shows something else. The universe wasn't built as a stage for life. It's not a garden. By overwhelming volume, it's silent, it's cold, it's empty. The brilliant galaxies, the nebulae, planets that might hold life, those are the rare exceptions. They're tiny islands, fragile, in a sea of nothing so vast we can't really grasp it. And that challenges a very old instinct, the idea that we're central. That the cosmos revolves around our existence, our consciousness. The void doesn't offer that comfort. It's the final argument against a universe centered on us. But this nothingness, it's not just an absence, it's not a passive backdrop. It actively shapes everything, the something. The galaxies, the stars, us exists in this form because of the void. The great walls of the cosmic web are defined by the emptiness around them. Their structure is a dialogue between presence and absence, so this void makes us reconsider nothing. Nothing isn't a blank slate. It's a positive feature of reality. It has gravitational influence. It has a history of expansion. It leaves an imprint on the oldest light. Nothing, in a cosmic sense, is something, and thinking about that can bring a deep response. It's a modern echo of what Pascal felt, the eternal silence of infinite spaces. The dread facing a billion light-year emptiness. It's easy to feel insignificant. Our entire history, every triumph, every tragedy, every work of art, every act of love, all on a speck of dust, on the edge of a galactic island, drifting on the shore of an infinite desert. That perspective feels cold. But the same perspective can also create awe. The fact that we're here at all, on this tiny island, with minds that can measure the void, that can trace its shadow, that can feel its weight, it's astonishing. Our insignificance in scale is matched by a significance in capability. We are the universe in one of its rarest forms. Trying to understand itself, the void makes our island of matter not less valuable, but more precious. It's a rarity, a cosmic accident of staggering improbability. So understanding the universe isn't just about charting the something. It requires us to grapple with the profound reality of the nothing, honestly, humbly. It's in that tension, between our island home and the surrounding silence, that our deepest questions about existence truly begin. The idea of a great emptiness has been with us for a long time. People looked at the night sky long before telescopes and wondered about the space between the stars. In ancient India, Buddhist thinkers had a concept called sunyata. Emptiness, voidness, but this wasn't about physical space. It was a philosophical principle. It said that all things are empty of a separate, independent existence. Everything is interconnected, so the void wasn't just an absence. It was a fundamental characteristic of how everything relates, a principle woven into reality itself. Then, in ancient Greece, the atomists like Democritus and Leucippus had a different idea. They imagined the universe made of tiny, indivisible particles. Atoms, and the void was the infinite, empty space where these atoms moved and combined. For them, the void was a necessary stage. Without emptiness, they reasoned, there could be no motion. No change, no creation, so you see a pattern. Across these early cultures, the human mind kept returning to the concept of the void. It was a placeholder for the unknown, a necessary counterpart to matter, a tool to explain how things come to be and pass away. This thread continued into modern science. In the 16th century, the astronomer Thomas Digges challenged the prevailing model. He proposed a radical idea, that the universe was infinite, and that the stars were scattered without order throughout a boundless void. This was a staggering leap. It replaced a small, ordered universe with an infinite, star-studded emptiness, a vision of cosmic scale. For a long time after that, the void remained mostly theoretical, an assumed backdrop. The great achievement of astronomy was filling that void with objects, cataloging stars, discovering nebulae. The emptiness itself wasn't the subject. It was just the canvas. Everything changed in the latter half of the 20th century. This was the shift from assumption to measurement. Astronomers began conducting large-scale surveys of galaxy positions. They were taking a census, and when they plotted the locations of millions of galaxies in 3 dimensions, the pattern that emerged was breathtaking. It wasn't a random scatter, it was a web. A vast cosmic web of filaments and clusters, and the most striking feature wasn't the bright knots where galaxies gathered. It was the enormous, dark bubbles in between, the voids. They weren't philosophical abstractions anymore. They were measurable, mappable realities. Giant regions, hundreds of millions of light-years wide, containing almost nothing. The discovery was transformative. It meant that emptiness had a specific shape, a structure, a geography. The void was no longer a passive stage. It was an active, dominant component of the universe's architecture. This journey, from the philosophical void of Sunyata and atomism to the mapped supervoids we see today, is a story of human perception. Our tools extend our senses. They allow us to quantify what was once only contemplated. We've taken an ancient concept, the great nothing, and given it dimensions. We've measured its gravitational influence, traced its effect on light, understood its role in shaping everything else. The supervoid represents the culmination of that long journey. It is the philosophical void made concrete. A billion light-year-wide testament. To truly understand the something of our universe, we must first learn to see and to measure the profound reality of the nothing. The largest structures in the universe might be communicating. That's the alignment enigma. It's a simple question: are the great voids connected? Not by galaxies, but by some invisible geometry. A hidden pattern in how they're arranged. For a long time, cosmology has relied on a principle: isotropy. The idea that on the largest scales, the universe has no special direction. It should look the same everywhere. The cosmic microwave background is our best evidence. It's incredibly smooth. But then you look at the distribution of the biggest emptinesses, and a subtle pattern might emerge. Some studies have suggested this. They look at the positions and shapes of the biggest supervoids, and they find hints. These colossal bubbles of nothing might not be random. Their elongated shapes, their major axes, might point in similar directions. Even more startling, this alignment might connect to the universe's own motion. We're all moving. Our galaxy, our local group, is being pulled toward a great attractor. That creates a dipole, a hot and cold pattern, in the cosmic microwave background. The suggestion is the voids align with this grand flow. If that's true, it's not just a curiosity. It's a potential violation of a bedrock assumption. It would mean the universe has a grain, like wood, on the largest scales we can measure. A preferred direction woven in from the beginning. So where would that come from? The leading theories go back to the start. The inflationary epoch. That hyper-expansion was supposed to smooth out any initial irregularities. But maybe some primordial seeds, some asymmetries, were etched so deeply that inflation couldn't erase them. These could be pre-inflationary fossils, anisotropies from before time as we know it began. They would have stretched to cosmic size, imprinting a subtle directionality on everything after. The voids, as the dominant volume-filling features, would be the clearest tracers of this ancient pattern. There's another possibility, more fundamental. It suggests the laws of physics themselves might have a slight directional bias at the grandest scales. A cosmic asymmetry built into the vacuum. This isn't about things moving. It's about the stage itself having a subtle warp. Proving it is a huge statistical challenge. You have to map thousands of voids across vast distances. Measure their orientations with incredible precision. Then run complex algorithms to see if any alignment rises above random chance. It's like trying to see if a field of scattered logs all fell from trees leaning the same way. You need a huge sample, very careful measurement. If the Aridanus supervoid is part of such a pattern, its significance grows. It's no longer just a rare, cold anomaly. It becomes a key piece in a larger puzzle. A single bone in a cosmic skeleton whose arrangement tells a story of a universe born with a whisper of direction. This enigma makes us question uniformity. Our entire understanding is built on the assumption we're not in a special place, that the universe is homogeneous and isotropic. But what if, when we finally map the emptiness in enough detail, we find it isn't? What if the voids themselves draw a map that points somewhere? The search for this alignment is a search for the universe's deepest signature. A signature that might have been written before the first star ever shone. Detecting an absence is a profound technical puzzle. You can't just point a telescope at a dark patch of sky and call it empty. The real challenge is defining the edge of nothing, where the cosmic web ends and where the void genuinely begins. It requires mapping the positions of millions of galaxies with extreme precision, across billions of light years. Surveys like the Sloan Digital Sky Survey gave us the first three-dimensional charts. But to find a supervoid, you need depth. You need breadth. You need to see the faintest galaxies at the farthest distances, just to be sure you're not missing them. Because a single, sparse filament of galaxies crossing the void could make it look like several smaller bubbles, instead of one colossal emptiness. The line between one vast desert and a cluster of empty valleys is blurry. It's only discernible through painstaking statistical analysis of galaxy densities. Then there's the cold spot in the cosmic microwave background. That ancient light has traveled for over 13 billion years, and it passes through everything. Dust in our own galaxy, the faint glow of distant gas, even the subtle emissions from our instruments, all of that creates noise, and a random fluctuation in that noise can look, for a moment, like a cold spot. Distinguishing a true cosmological signal from this foreground clutter is like trying to hear a single, specific whisper in a roaring stadium. So scientists build exquisitely sensitive instruments, like the Planck satellite. They process the data with algorithms designed to peel away every known source of interference, and they're left with a purified map of the primordial sky. Where a feature like the cold spot either remains or vanishes, the true confirmation comes from correlation. It's the alignment of two different stories. One story is told by the galaxy surveys, a map of where matter is not in the modern universe. The other story is told by the CMB, a map of a temperature dip in the ancient light. When these two independent maps, created from completely different wavelengths of light and different epochs of time, show the same giant patch of sky, the case strengthens. It's like two witnesses describing the same suspect from different angles. One saw the shape of the emptiness today. The other saw its shadow on the wall of time. This work requires a fusion of disciplines: observational astronomy to collect the light, astrophysics to understand the behavior of galaxies and the expansion of space, statistics to separate signal from noise with confidence, and cosmology to tie it all together into a coherent picture of the universe's structure. It turns the philosophical concept of nothing into a quantitative science. We're not just staring into the dark. We are measuring its dimensions, weighing its gravitational influence, tracing its history. The fact that we can do this at all, that we can transform the challenge of observing what isn't there into a precise and meaningful measurement, is one of the great triumphs of the human drive to understand. That careful mapping, though, is only the start. The next group of cosmic mapmakers is already working, with tools that will turn those faint outlines of voids into sharp, clear territories. The Euclid Space Telescope launched in 2023. It's a huge leap forward. Its job isn't to look at single bright objects. It's to survey the whole sky with a wide, deep view. Over 6 years, Euclid will chart the positions and shapes of billions of galaxies. It'll build the most detailed 3D map of the large-scale structure we've ever had. With that map, the cosmic web comes into a focus we've never seen. The filaments get traced with incredible precision, and the voids, those great empty bubbles, get revealed in all their sprawling, intricate detail. We'll see their true shapes, their internal textures, how they connect to each other. The clarity will make our current understanding look like a rough sketch. On the ground, another giant eye is getting ready to open. The Vera C. Rubin Observatory in Chile will soon start the legacy survey of space and time. That's a 10-year project. It will image the entire visible southern sky every few nights. It creates a dynamic map, a living map of the cosmos. Its power is in both depth and repetition. It will find galaxies so faint and distant they're invisible now, pushing the edges of our void maps further out in space and further back in time. But more importantly, by watching the same sky over and over, it can measure subtle changes. That lets astronomers do more than just map where voids are. They can watch how voids grow and evolve. We'll see, in near real time on a cosmic scale, how dark energy stretches these emptinesses, how their edges shift, how they herd galaxies. This survey will find dozens, maybe hundreds of new supervoids. It'll build a statistical catalog that finally tells us if the Aridanus void is a rare fluke or a common part of cosmic architecture. To read the shadows these voids cast, we need an even sharper view of the ancient light. The next wave of cosmic microwave background experiments is built for that. Projects like the Simons Observatory, a set of powerful telescopes in the high Chilean desert, will map the CMB with sensitivity and resolution far beyond what we can do now. It will scrutinize the cold spot in Aridanus like never before, dissecting its temperature patterns to tell the difference between the subtle imprint of a supervoid and the possible, more exotic signatures of something like a cosmic texture. It will also find and study hundreds of other cold and hot spots, cross-referencing them instantly with the new galaxy maps from Euclid and Rubin. That cross-referencing on a massive scale turns speculation into solid statistics. We'll know, with definitive evidence, how the emptiness of today connects to the whispers from the beginning. We're at the threshold of a new era in understanding the universe. For centuries, astronomy focused on the bright points, the stars, the galaxies, the dazzling events. Now we're turning our most powerful instruments toward the dark spaces in between. We're learning to chart the voids with the same precision we once used for the glittering cities of stars. This shift in perspective promises more than new data. It promises a fundamental rewriting of our cosmic story. A story told not only by the light that is, but by the profound and shaping silence that is not. This brings us to the sixth mystery, the void's lifetime. How long does a structure made of nothing actually last? You might think of these emptinesses as permanent, but they are not. They have a life cycle, a birth, a maturity, a fate. In the early universe, right after the cosmic microwave background was released, the seeds were already planted. Those slightly underdense regions, the cool spots in that ancient light, they were the embryos of future voids. And over billions of years, gravity did something strange. It worked in reverse here. Instead of pulling matter together, the slightly emptier regions pushed matter away. Neighboring small voids merged like soap bubbles combining. They swallowed the tenuous filaments between them. They grew. That's how a supervoid is born, through a cosmic consolidation of emptiness. Its lifespan is tied directly to two great competing forces. On one side, you have gravity from the surrounding cosmic web. The dense filaments and walls around the void exert a pull. They could, in theory, slowly siphon matter back into the emptiness. Fill it in over eons. On the other side, you have dark energy. Its repulsive push causes the void's interior to expand faster than the universe at large. This stretches the void, makes it larger and emptier, actively resisting any infall of matter. For a typical void, this is a tug of war. But for a supervoid, a billion light-year-wide giant, the balance tips dramatically. Its scale is its shield. The gravitational pull from the distant walls is incredibly weak across that vast gulf. Meanwhile, dark energy's influence inside that immense volume is overwhelming. The void isn't just holding its ground, it's winning. It is growing and becoming more empty. So what's the lifespan of such a structure? Given its size and the dominance of dark energy, a supervoid like the one in Aridanus could be one of the most enduring features in the entire cosmos. While stars will burn out, galaxies will merge and fade, this emptiness may persist. Its lifetime could span tens of billions of years, far longer than the current age of the universe. It will likely outlive every star that shines today. Its evolution offers a direct preview of the universe's own far future. As dark energy's influence grows, the cosmic web will be stretched and torn. The great filaments will snap. Galaxy clusters will become isolated islands, and the voids, these expanding bubbles of nothing, will merge into a single, all-encompassing void. The supervoid we see today is a precursor, a glimpse of the ultimate destiny of all structure. Studying its dynamics is like reading a biography of cosmic emptiness. From its whispered beginnings in the first light, through its aggressive growth phase as it consumes smaller voids, to its long, slow maturity as a dominant, accelerating feature. Its life cycle mirrors the universe's journey, from a dense, hot beginning to a cold, thin, and silent end. This supervoid is not just a place, it's a chapter in a story billions of years long, showing us that in the cosmos, even nothing has a history, and a future written in the relentless expansion of space itself. The seeds of emptiness were planted in the very first instant. In that first fraction of a second during inflation, the universe didn't just grow. It ballooned. It expanded at an exponential rate. And in that energetic vacuum, quantum mechanics says there were constant fluctuations. Tiny ripples, particles and energy flickering in and out of existence. Normally, these are microscopic, but inflation acted like a cosmic magnifying glass. It took those quantum ripples, the tiny underdensities and overdensities, and it stretched them. It stretched them across the entire sky. A subatomic whisper became a macroscopic feature, billions of light years across. The slightly denser spots became the seeds for galaxy clusters, and the slightly emptier spots, the underdensities, became the seeds for the voids. So the supervoid we see now, it isn't a random accident. It's likely the grown-up version, the fully evolved version of one of those primordial underdensities. A quantum hiccup, magnified to a cosmic scale. That connection is profound. It means the void is a living fossil, a time capsule from the universe's first trillionth of a second. And by studying its properties, its exact size, its depth of emptiness, its shape, cosmologists can run a test. They can ask if our models of inflation are right. Do they predict the correct spectrum of those initial fluctuations? Did inflation produce the right mix of seeds to grow a void this vast? Or does this colossal emptiness suggest something else? That the early expansion was even more dynamic, that it followed a different set of rules. The void becomes a diagnostic tool. Its vast, quiet expanse holds encoded information. Information about the most violent, energetic moment in all of existence. We're reading the story of creation, but not in the light of the first stars. We're reading it in the organized absence of matter. This turns our understanding inside out. The largest structures we see are direct imprints of the smallest phenomena we can conceive. The void is the bridge. It links the quantum world to the cosmic scale. Every measurement we make of its emptiness is a measurement of those first instants. So when we chart its boundaries, we're not just mapping a desert. We're calibrating the magnifying glass of inflation itself. The silence of the void speaks directly of the roar that began everything. The human need to understand the void has always been in art. Long before telescopes could measure it, painters and writers were already feeling its emotional weight. They sensed the scale, they felt the silence. Caspar David Friedrich, the German Romantic painter, he didn't paint galaxies. He painted a single figure on a mountain peak, looking out into a vast, misty abyss, or into an endless, starry night. His work captures the sublime, that feeling of awe mixed with a touch of dread before something overwhelmingly grand. That mixture of wonder and insignificance. It's the same feeling a modern astrophysics paper describes when it details the Aridanus supervoid. Friedrich's canvases are like a pre-scientific echo of that data. A cultural premonition of the cosmic emptiness we now map. Literature went into this terrain with more visceral terror. H.P. Lovecraft built his entire mythology on cosmic indifference. His stories have these vast, ancient beings, gulfs of space so immense they shatter the human mind. The fear in Lovecraft isn't about monsters with claws. It's the fear of the emptiness itself, an uncaring universe where humanity is just an irrelevant speck. Stanley Kubrick's film 2001, A Space Odyssey, translates this perfectly. The famous Stargate sequence. It's not a journey to a place filled with things, it's a plunge into a psychedelic void. A confrontation with the infinite and the incomprehensible. The chilling silence of space in that film, broken only by human breathing. It makes the emptiness a character you can feel. What's remarkable is these artistic visions aren't just metaphor anymore. They have a scientific counterpart now. The supervoid is their real-world anchor. When an artist shows a character trembling before an infinite abyss, we can point to the sky and say it is there. That abyss exists. It has a temperature, it has a size, a gravitational influence, the cosmic awe and the existential dread in paint and prose. They're validated by the cold, hard data of cosmology. This doesn't diminish the art. It deepens it, it creates a dialogue. Science provides the facts of the emptiness. Art provides the language for our emotional response to it. Together, they give a fuller picture, engaging the intellect and the spirit. This interplay reminds us that exploring the cosmos is never just a technical act. It's a profoundly human one. We send out probes and build telescopes not just to collect data points, but to answer ancient questions about our place in the grand scheme. The void challenges that search for place. It whispers that we are alone, adrift. Art has always given voice to that whisper, giving form to the formless fear. Now science has given that whisper a location, a physical explanation. This cultural resonance enriches the discovery. It means when we study a supervoid, we're not only charting a region of space. We're also navigating a landscape of human meaning and fear and wonder that we've carried for centuries. The void on our maps is the same void that's haunted our dreams, inspired our greatest works, proving the journey to understand the universe is ultimately a journey to understand ourselves. 70 microkelvins, that's the measurement. A cold spot in the ancient light, just 70 millionths of a degree below the cosmic average. To us, that number doesn't mean much. It's too small to feel. But in the cosmos, it's a shout, a real anomaly, because the cosmic microwave background is incredibly uniform, almost perfect, 2.725 Kelvin everywhere. The usual variations are tiny, just static, fine-grained, but this is different. This cold spot is large, coherent, a broad, gentle bowl of chill in that primordial glow. And that's what matters, the odds. The chance of a fluctuation that large, that cold, appearing at random in such a smooth field, it's incredibly small. So it demands a cause, an explanation on a cosmic scale. We quantify it, 70 microkelvins, but then you think about what that number means in energy. The scale of it. This chill isn't a point. It's spread across a huge patch of sky, hundreds of times larger than the full moon. And when you add up that tiny temperature deficit over that immense area, and then translate it into the volume of space, the void actually occupies. The number becomes staggering. The total energy missing from that light is colossal, a vast deficit, a debt paid by trillions upon trillions of ancient photons crossing that great emptiness. That precise quantification is the key. It's what lets scientists test the Integrated Sachs Wolfe effect. The theory predicts a specific cold spot, given the estimated size and depth of the supervoid. 70 microkelvins is right in the ballpark. That match prediction and observation, it turns an idea into a compelling theory. Measuring it, though, is an exercise in extreme precision. Like trying to hear one specific whisper in a silent room, knowing the room itself has a faint, constant hum. The instruments, like the Planck satellite, had to be cooled to a fraction of a degree above absolute zero. Just to avoid adding their own heat to the signal, they mapped the entire sky over and over. Subtracting the glow of our galaxy, the radio whispers from quasars, every known foreground. What was left was the pristine map of the infant universe. And there, in Aridanus, this subtle, persistent chill. That precise temperature dip is more than data. It's a cosmic fingerprint. It directly connects the architecture of nothing, the void's sheer scale, its gravitational profile, to the fundamental journey of light. It shows how the gravity of an absence, evolving over billions of years under dark energy, can leave a permanent mark on the first light. That 70 microkelvin whisper is the smoking gun. It tells us the void isn't just there. It's actively, measurably, shaping the story written in the sky. That whisper of cold takes us to the edge of known physics, and then asks us to step beyond. Could the supervoid be more than a natural structure? Could it be evidence for a multiverse? This is where cosmology meets its most speculative frontier. The theory of cosmic inflation says our entire observable universe expanded from a tiny, energized patch. But if that can happen once, it could happen many times. In some models, the larger reality is a frothing sea of spacetime, constantly giving birth to new bubble universes, each with its own laws, its own physics, completely separate from our own. But in that chaotic foam of the earliest moment, what if two bubbles expanding at nearly light speed brushed against each other? A collision between universes. The energy released would be unimaginable. It would send shockwaves through the fabric of each newborn cosmos. And that collision, theorists suggest, could leave a lasting scar. A distinct, circular imprint on the cosmic microwave background of each universe involved. A region where the primordial plasma was disturbed or cooled or stretched in a specific way. That imprint, from our point of view, might look exactly like a large, anomalously cold spot. So the void we map today, the emptiness we measure, could be the three-dimensional aftermath. The grown-up shadow of that ancient cosmic bruise. It would be a fossil of a traumatic encounter with another reality entirely. This idea is highly speculative. It sits at the very limit of testable science, but its power is in its audacity. It takes a stubborn anomaly in our data, a cold spot that resists simple explanation, and connects it to one of the most profound ideas in modern theoretical physics. The void becomes a potential bridge, a tangible, observable feature in our sky that might be a window into a cosmos vastly larger than our own. It shows a principle in science. The most extreme structures, the great outliers and anomalies, often serve as the best testing grounds for our most ambitious theories. They stress our models to the breaking point. They force us to ask if our map of reality is complete, or if we need a bigger map. The Multiverse Hypothesis is the biggest map imaginable. And right now, the Supervoid is one of the very few places in our observable universe where we might look for a fingerprint from that vaster reality. Whether it is a scar or not, the possibility alone reframes the emptiness. It transforms a cold, silent desert from a mere absence into a potential message. A cosmic clue waiting in the dark that our universe may not be alone. The cosmos is so large it becomes abstract, numbers that are too big to really grasp. But you can bring it down to a human scale. Take the whole observable universe, all 93 billion light years. Shrink it down to the size of the Earth. On that cosmic Earth, a galaxy like ours, the Milky Way, would be smaller than a grain of sand. A big cluster of galaxies, a whole city of stars, would be about the size of a major city. And then there's the Aridanus supervoid, that huge emptiness. On this scale, it becomes an ocean basin, something like the Pacific Ocean, covering almost a third of the planet. But imagine that basin is dry. A vast continental depression, a bowl of near-perfect nothing, with just a few scattered grains of sand, lone galaxies lost on its floor. That's the void, that's the scale, and that comparison does a couple things. It makes the isolation tangible. We're not just on a pale blue dot. We're on a speck of dust, adrift on the shore of a Pacific Ocean of emptiness. The nearest island of matter is an unimaginable journey away across that dry sea. It gives a stark, geographical clarity to where we are. And second, it shows the sheer size of what we're now mapping. We're measuring features that, on this map, are continents and oceans, structures so vast that light hasn't had time to cross them since the beginning. That perspective is humbling. It confronts you with a universe not built to our measure. All of human history, every civilization, every life, happens on that single, microscopic grain of sand. The cosmic ocean doesn't notice, but then, that same perspective is also empowering, because it's our human minds born on that grain of sand that conceived of this map. We built the tools to measure the depth of that dry ocean. We traced its influence on the oldest light. We comprehend realms so far beyond experience they should be invisible. We took the infinite and gave it a shape we can talk about. That's the quiet triumph inside the awe. The universe may be indifferent, but we are not. We're the part that turned around to look back, to measure the silence and feel its weight. And in doing that, we've made the immense emptiness in a way knowable. Why study emptiness? It seems like a philosophical question, but we build telescopes, launch satellites, run supercomputers, all to map a place where there's almost nothing. The reason isn't about immediate returns, it's about knowledge. To understand the universe, you have to understand all its parts, and the voids aren't minor. They're the dominant volume. Ignoring them would be like a biologist ignoring the circulatory system and only studying the heart. They're integral. So studying them tests the pillars of cosmology. It tests Einstein's gravity on the largest scales. Does it behave as predicted inside a billion light-year region of near nothingness? It tests dark energy. Is its push constant, or does it vary, which we might see in how these colossal bubbles grow? It tests inflation. Do the patterns of emptiness match the quantum seeds stretched in that first instant? The void is a natural laboratory, one we could never build. It runs experiments on fundamental physics across billions of years. We just have to learn to read the results. This pursuit pushes our technology. Mapping nothing requires seeing everything around it with exquisite precision. That drive has led to advances in detector sensitivity. In cryogenics, cooling instruments to near absolute zero. In algorithms powerful enough to process petabytes of data. These are technological spin-offs. A quiet, practical benefit of pure curiosity. The chips in our cameras, the fiber optics, the software that guides our lives, many have roots in that push to see further, to measure more faintly. Studying the void doesn't just tell us about space. It refines the tools we use here. But beyond utility, even beyond knowledge, there's a deeper driver. It's the same instinct that made our ancestors gaze at the stars and tell stories. It's the human drive to explore, to push back the boundary of the unknown. To look into the deepest, darkest, most silent corner of reality and ask what it is, what it means. Studying the void is an act of intellectual courage. It's facing the cosmic abyss not with the fear it once inspired, but with the steady light of curiosity. It's a declaration that we will seek understanding everywhere. Not just in the brilliant, welcoming light of stars, but in the cold, expansive silence between them. This journey illuminates more than the cosmos. It illuminates our own place within it. By daring to measure the void, we affirm that our search for meaning isn't diminished by scale. It's defined by it. We choose to know the universe in its entirety. The brilliant islands of matter, and the vast, shaping sea of nothing that holds them. This journey ends where it started, at the edge of a profound silence. We trace the shadow of a void so immense it leaves a chill on the oldest light we can see. We followed the science, from a subtle cold spot in the cosmic background to the discovery of a staggering emptiness. A void spanning nearly 2 billion light-years, and we unraveled the physics of how an absence can push. The Integrated Sachs Wolfe effect. It allows a void to drain energy from ancient photons, cooling them on that long journey to us. This single structure, a supervoid, has challenged the predictions of our best cosmological models. It pushes us to ask if it's a rare fluke, or a sign of deeper, undiscovered laws. It's even inspired speculations that reach beyond our universe, into realms of cosmic collisions, into multiverses. And through all this, the exploration reveals a fundamental truth. The cosmos isn't defined by matter alone. It's a tapestry, a dynamic balance between the brilliant threads of galaxies and the vast, dark fabric of the voids stretching between them. The absence of something is not passive. It's an active, shaping force with gravity, with history, with consequence. In its immense indifference, the void offers a humbling perspective. It reminds us our world is a rare and precious island in a sea of cosmic silence. But it also showcases the extraordinary reach of the human mind, that from our tiny island, we can map these oceans of nothing. We can weigh their influence, ponder their meaning. The universe may be indifferent, but our curiosity is not. These great emptinesses are not the end of the story. They are invitations, each unanswered question about their alignment, their origins, their ultimate fate. It's a frontier waiting for the next mapmaker, the next theorist, the next observer who will point a telescope at the dark and dare to ask what it holds. The exploration never truly ends, it just finds a new direction. In the quiet spaces between the stars,